Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the quantum theory and photon. In our last lesson, we learned about atomic spectra. We learned that the unique atomic spectrum of each element varies depending on temperature, pressure, and magnetic field strength. Therefore, they can be used to help astronomers learn more about the surface and surrounding atmosphere of stars and planets far from Earth. In today's lesson, we will define the term photon as a unit of light energy. We will explain the quantum theory and discuss how quantum theory explains the photoelectric effect. We will also discuss the relation between photons absorbed and electrons released during the photoelectric effect. In 1900, a German physicist named Max Planck proposed a new theory about matter and energy. He believed that a hot, glowing object was only able to give off or absorb a certain amount of energy. According to Planck's theory, the energy of the radiation is represented by this formula. E represents the energy of the radiation. N is a positive integer, which is referred to as a quantum number. Nu is the frequency. And H is a proportionality constant, which is also called Planck's constant, and is equal to 6.626 times 10 to the power of negative 34 joule second. With energy in joules and frequency in seconds, H has units of joule second. Thus, according to Planck's theory, the rules seem to be different when we are dealing with the loss or gain of energy from atomic or subatomic particles, as compared to when we are dealing with objects of ordinary size. His theory went against the classical laws of physics, which stated that radiation was continuous and therefore had any possible energy value. According to Planck's quantum theory, there is such a thing as a smallest allowable gain or loss of energy. This gain or loss had to be a whole number multiple of a constant multiplied by the frequency of the radiant energy. Delta E represents the amount of energy that is gained or lost. H nu is the quantum energy, or the smallest amount of energy at a given frequency. Planck's theory would revolutionize the way the physical world is perceived. Students, in groups of 3 or 4, please discuss Planck's theory. Explain how it revolutionized classical perceptions of the nature of energy.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. I am sure that you had some interesting discussions. Planck's theory suggested that there is such a thing as a smallest allowable gain or loss of energy. Prior to this, it was believed that all energy was continuous and without limits. Let us continue with our lesson by discussing the photoelectric effect. When light shines on a clean metallic surface, the surface can emit electrons. This is known as the photoelectric effect. For each metal to emit an electron from its surface, there is a minimum frequency of light called threshold frequency. Below this frequency, no electrons are emitted. In 1905, Albert Einstein explained the photoelectric effect using the quantum theory. He assumed that the radiant energy that strikes the surface of the metal does so in tiny packets. He referred to these energy packets as photons. Each photon is a quantum of energy, which is represented here as h nu. EPH denotes the energy of a photon. Thus, radiant energy has limited values. Photons that have high frequency radiation have high energies, and photons that have lower frequency radiation have lower energy. When photons are absorbed by metals, their energy is transferred to electrons that are in the metal. A certain level of energy is needed to allow the electron to overcome the attractive forces that hold it within the metal. If the energy is sufficient, the electron will be ejected from the metal. If the photon has more than the minimum amount of energy required, the extra energy will appear as the kinetic energy of the emitted electron. In this equation, EK represents the kinetic energy of the emitted electron. EB is the energy that binds the electron to the metal. If we rewrite this equation using EK equals 1/2 me nu squared and EB equals h nu O, we end up with this equation. Me represents the mass of an electron, and nu O is the threshold frequency. Thus, the more energetic a photon is, or the higher its frequency is, the higher the velocity of the emitted electron will be. Let us pretend that we have two beams of light. They have the same frequency, which is greater than the threshold frequency, but different intensities. The beam of light with the higher intensity will have a larger number of photons than the beam with lower intensity. As such, it will also eject more electrons when shown on the surface of a metal. Students, what observations can we make regarding the nature of the photoelectric effect?
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello, students. I wonder what observations you came up with. You might have said that the more intense the light, the greater the number of electrons emitted by the target metal. Perhaps you also said that the higher the frequency of the light, the greater the kinetic energy of the emitted electrons will be. Both observations are correct. These observations can be quantified by this equation. Nu O represents the threshold frequency. Me is the mass of the electron, and nu is the velocity of the emitted electron. The energy of a quantum of radiation that goes into ejecting a photoelectron out of the metal, as well as the energy that binds it to the metal, gives us the kinetic energy. Students, I am sure you are wondering how the photoelectric effect can be put to use in the real world. A photoelectric cell, also known as a phototube, is an electron tube in which the electrons initiating an electric current originate by photoelectric emission. These cells can be used to detect radiation, which is extremely useful during nuclear research. They are also used more commonly in televisions, burglar alarms, traffic light controls, and in photosensor motion detectors. In our lesson today, we defined a photon as a unit of light energy. We explained how quantum theory explains the photoelectric effect. We also discussed the relationship between the photon that is absorbed and the electron that is released during the photoelectric effect. This is all for today. Until next time, thank you, teacher. Thank you, students.